in this session, we will do problems. So we will do 4 problems. Just to clarify, A bar means A complement. A bar is A complement. So the first question is asking you to find if they are mutually exclusive. Probability of A is 0.4, probability of B is 0.5. It's asking you to find probability of A union B, probability of A complement, and probability of A complement and B. So what is the question? Question number 1 was the following. I said A and B are mutually exclusive. So A and B are mutually exclusive means A and B intersection is empty, right? And I told you probability of A was 0.4. And I said probability of B was 0.5. Right? Maybe I'll turn my video on so you can just see my face just in case. Or maybe we'll come back to it later. It's 0.5. And it asks you to find probability of A union B. That was the first question, right? So the answer for that is quite easy, right? Because by the axioms of probability, you know that in my notes I've shown you a theorem which says if A and B are empty, intersection is empty, then probability of A union B is just the sum of the probability. Right? The probability just sums up. So probability A and B in this case would just be 0.9. Very nice. So A was easy. B should also be easy. B is just says probability of A complement. Right? So A complement. What is it? But again, by the axiom of probability, you know probability of A complement is just 1 minus the probability of A. And that's going to be just 1 minus 0.4, and that's 0.6. Very nice. That's an easy question. The next one was C was, I asked you was probability of A complement and B was what I asked you. Right? So here, what do you do is, so A complement and B, right? But A and B are empty, people. So first you observe is probability of B is the same as probability of B and A union probability of union the set B and A complement. Now these two sets are mutually exclusive, right? Because what's in B and A complement cannot be in B and A. This is going to be equal to probability of, let me erase this, that is in blue, sorry. Come on. Probability of B and A you go down and this B and A is empty. So probability of empty set plus probability of B and A complement. But probability of empty set is 0. So probability B is just the probability of B and A complement. But that's what you wanted to find, right? B and A complement. But B and A complement is as probability of B, but probability of B was given to us as 0.5. So it's 0.5. Therefore, as probability of B is 0.5, sorry, my handwriting is sometimes very bad, 0.5, this implies that probability of A and B, A complement and B is 0.5. So that's the first solution. Okay, let me go to the next question. So here, in this question, it's quite easy, right? Because let me write the answer down for A. See, we already know probability of A plus probability of B, right? That's going to be, you can decompose A into 2 parts and B into 2 parts, right? So probability of A and B complement union, like we discussed before in the previous problem, union A and B plus probability of B as B and A complement union B and A. Right? Very nice. So now once you do this, they're all mutually exclusive events. So this is going to be equal to probability of A and B complement plus probability of B and A complement plus twice probability of A and B. Because these two will give you A and B. Very good. So once you have that, you're kind of done because uh, this is A and B complement plus B and A complement plus twice probability of AB would just give you. Um, so maybe I'll leave it as is just going to be less than or equal to 1 plus probability of A and B, no matter what you do. Yeah, very nice. Because I could just throw a 1 AB and then get this 1 plus A. So why is this true? Why is inequality true? That's because if you observe, I didn't write it properly here. I just said it orally. Because 1 is the same as probability of A and B plus probability of A and B complement plus probability of A complement, A and B complement, and then A complement and B complement plus probability of B complement and B. That's how I would get that. Right? So, hence, you would get this exactly this. Right. How do we do part B now? Part B is the same. The idea is the same. Probability or should probably exactly one of the two events occurs, right? So what does that mean? Probability that exactly one of the two events occurs is going to be what now? That's the same as probability A and B does not occur as B complement, or A does not occur, that is A complement happens and B. That's what B is. But these are mutually exclusive events. So same as probability of A and B complement plus probability of A complement and B, right? And you will get that's exactly what you have here, right? But now you again split it, right? You just have to just be a little careful. You just have to add an A and a B. So you just probability A and B complement plus I'm just going to add this extra term here. What happened? I'll add a probability of A and B. Okay? I'll leave this as it is. And I'll also add an A and B. But since I've added 2, I subtracted 2 and A. So now if you look at these two guys, A and B complement and A and B, A complement and B and A and B, if you look at these two guys, these are just going to be, this is just probability of A, and this is just probability of B, and this comes down as probability of A minus. A and B. So both 2A and 2B are true. So I've written the question again in the next page. I'll show the question to you. So read the question. What's the question? The question says a ball contains M balls, out of which W are white. Okay, W. So that's a key feature of the ball. So W of them are white. There are total M balls in the box. Okay, that's clear. Very good. Now, what I go and do? I go and sample N balls. Very nice. N balls. And the key feature is I go and sample them with replacement. With replacement. Let me color it differently so I can sort of see differently. Let me take this color. I like this color. It's with replacement, right? So when I pick a ball up, I put it back inside. So next sample. And let AJ be the event that the ball drawn on the jth draw is white. So AJ is the event, J is some number to 1 and N, AJ. What's crucial here is that B sub K is the event that the sample of N balls contains exactly K white balls. Okay? And I'm asking you to find the conditional probability of choosing a white ball on the jth draw, given that you are allowed to choose only k people of white balls in all the n draws. Okay, that's the key. That's the key question. Right. So, is the question is clear? Can someone tell me it's clear to them? Or if it's not clear, can you just say it's not clear? Maybe you can send on chat if I read the question correctly. The question is clear, right? You have to find the chance that you have in the jth draw, you draw a white ball, but you're given that in all k people, you only have all n people, you only have k white balls. Right. So let me try and solve this for you. Okay. So this is a key feature of probability. You must know how to write things down. Then it will come automatically. The solution will come automatically. So here everybody has got it. See, in any draw, the box remains the same. It always has W balls, out of which M are white. Right? So let me say let P be equal to W by M. And this is the probability of AJ. Right? The probability of AJ is going to be equal to P, W by M. There's no, because at any draw, the box composition remains the same. I have W white balls. Each ball is equally likely to be picked. I have a total of M balls, so it's W by M. That's clear, right? Yes, it's clear. So this is because, why is this because? Because it is with replacement. With replacement. And each in the box, each ball is chosen equally likely, right? Each ball is chosen equally likely. Very good. That part is clear now. Now, I want to understand, this is true for every J. So let's go to the other guy. This is first calculation. Very good. The other person is, I look at B sub k, is that there are only k white balls in a sample of size n. Right? So you select k white balls are chosen in n draws. Right? So that means in k of the draws, I have white. In the rest n minus k, I don't have white. Right? So another way of doing it is that k balls are chosen in n draws, and this is implicit in the statement, which is what you have to observe, that n minus k balls are not white. Are not white in n draws. Right? So it's implicit in this slide. So B sub k is the event that k of them are white and n minus k of them are not white. But you know the chance of picking a white ball in each step is just p. So that means there's another way of thinking about this is that you could think about this experiment as you think of choosing a white ball as a success. You think of it as you want k successes in n trials with probability of success equal to p, which is W by. That's what this amounts to. Because you're going to define the chance of choosing a white ball as success, and you want k of them in n draws, and the rest n minus k, you don't want to choose a white ball. But this we know from binomial probability. You recall binomial probability, it's just binomial, right? You want k successes in n trials, it's just binomial NP. So therefore, probability of bk is going to be equal to, binomial probability is what now? It's just n choose k, that you choose the k places in which you want success. And you want k of them, you want to have success, and you want the rest to have white, non-white ball, n minus k, no white. Is that clear? That's easy. This also is quite easy. That is, so far so good. Is it clear to everybody that this part until now should be clear, right? Everybody should do it again. So now what I've set up the things so far correctly. Probability of AJ is W by N. Probability of BK is N choose K, P power K, 1 minus P the power N. Very good. So far, so good. Now, we also know one more fact. Let's see. Suppose I tell you that the jth ball drawn is white. Okay? So if I look at probability of BK given AJ, how do I find that out? That means I know jth ball drawn is white, and I want K balls to be white in N draws. So can someone tell me? I'll write something down here. What should I write in the star? Let's say. So I have to have, let's say, the star 1. My claim is going to be this: star 2, p to the power star 3, 1 minus p to the power star 4. So let me write down these in red, so it's clear. So it's clear. Can someone in chat tell me what will be star 1 and star 2? The question is the other way around. That is correct, Kushal. But I'm doing this first calculation. Very good. It's very question the other way around. It's very good. It's very good observation. That I want AJ given BK, but first I have to find BJ given AK. So first thing is that what does this mean? That means the jth ball drawn. So we mark this in green. So it's I'll mark green. So this means that the jth ball drawn is white. You're given that. And what is this telling you? This is telling you that you have total of K people in N draws. That means this guy is already white, and in the others you have many things, and you want K of them to be N. So in total of N draws, in total of 1, 2, blah blah, this jth one is white, and then this an N, you want K of them to be white. But K of them to be white, given the jth draw to be white, make the following observation that this is the same as probability of having K minus 1 white balls in N minus 1 draws, because in the jth draw you button a white. Right? So that's just a simple calculation before. That's just N minus, that's the same as binomial of N minus 1p now. Because you have N minus 1 trials and you're looking at K minus 1 successes in N minus 1 trials. So that'll just be N minus 1 choose, sorry, write in black. Choose K minus 1. And I'll have here p to the power K minus 1 and 1 minus p to the power N minus 1 minus K minus 1. Very nice. Right, this is what I have. So now comes to Kushagra's question. Then I was doing something else. The question asked something else. What did the question ask you? The question asks you, what's the chance that of finding a white ball in the jth draw, conditional on the event that you choose only K balls that are white in N draws. So here you have to use a Bayes theorem or use the conditional probability formula. So this becomes, but since probability of BK is positive, probability of AJ given BK is probability of AJ and BK divided by probability of BK. That's by definition of conditional probability. But now I can flip this, right? This is AJ given AJ and BK, I write it in green. That's going to be equal to, at the top, I can write it as probability of BK and AJ. That's the same thing. Divided by probability of BK. So now this guy is equal to probability of, the top guy, I flip it. Instead of thinking of AJ given BK, I write as probability of BK given AJ times probability of AJ, the whole thing divided by probability of BK. So now it's clear to you why I did that problem. Then I go back. What do I go back and see? I go back and see everything. Probability of AJ is W by M. Probability of BK is this binomial probability. Probability of BK given AJ is another binomial probability. So come here, I write this as, this first person is N minus 1, choose K minus 1, P to the power K minus 1. And then I have 1 minus P to the power N minus 1 minus K minus 1. I'll write as N minus K. That's the top part. Maybe I should write it in green, the first green. Okay. and this let me write it in some other, let's say red. Okay. Then I have probability of AJ, which was just W by M, which is just P. Well, I'll think of it as P for the time being. The whole thing divided by probability of BK, which was now N choose K, P power K, 1 minus P to the power N minus K. Very good. Let's see what all cancels now. You have P power K minus 1, 1 minus P to the power N minus K, and P. So all these cancel off. So this, I take a black here. I take this guy and this guy will go with this guy. That's 2 times. And these are the same. The green and the green are the same. 1 minus P, N minus K, the top and the bottom. So these cancel off. That's good. So all I'm left with is N minus 1 choose K minus 1 and N minus K. N choose K. So that's easy, right? That's just N minus 1 factorial by K minus 1 factorial and I have N minus K factorial. Whole thing divided by N factorial, K factorial, and N minus K factorial. N minus K factorial. So what do I get? I cancel these guys off. I am left with, if I cancel N minus 1 and N, I left with an N at the bottom. If I cancel K minus 1 with K, I get a K at the top. So it's K by N. So probability of getting a white ball, given that you choose K balls in N draws, is K by N. Can someone tell me what's special about this formula? Can someone think about it? What is special about this formula? Right. Good observation. It is independent of P, independent of W and M. What else is independent of? That's very good observation. It's independent of W and M. So it doesn't matter what the box composition is, I'm always going to get K by M. It's also independent of one more quantity. Which one? Tell me. Can someone tell me what is independent of what quantity? Yeah, very good. Independent of J. So someone answers this now privately, independent of J. So the key thing is that the key observation is for all J equal to 1, 2, up to N, we observe that probability of AJ given BK is K by N. So it's like a uniform probability. Very cool. So let me recap a little bit. Let's see if we can get this thing live. Let me get this correctly. We can show you the screen doubly. Let me recap everything for you so you understand what's going on. If this is okay, we go back up all the way up. We start here. We'll come back to this second. Let's go step by step. So the idea was that we did was the following, that we said, fine. Sorry about that. The idea was we start off with M balls and we're choosing little n balls with replacement. That was the problem. And we're asked to find out what's the chance that the jth ball is drawn given that we're choosing K balls in n draws, K white balls in n draws. That was the question. So what did we do? We first said, fine, we're going to go and do the basics first. We're going to go and do the basics. But basically, what do you mean? We're going to go and say, fine, we will compute the chance of getting the white ball in any jth draw. And since we're doing with replacement, it doesn't really matter. It's always going to be W by N. That's the first calculation we did. The next thing we did was we had to understand how do we choose K white balls in N draws. But because we're doing with replacement, this becomes, I forgot one important point here, this becomes K successes in N independent Bernoulli trials. So that's important. Because I'm doing with replacement, this independence is kind of crucial. Let me put a different color there. Let me see. Let me put purple perhaps. So independence is crucial. So K N independent trials, because I'm doing with replacement, the boxes remain the same. So that means I'm just doing a binomial experiment. That's why I get N choose K, P power K, 1 minus P to the power minus K. I'm almost done, but I had to compute the probability. If I know what happens in the jth draw, what's the chance of BK? But this again by independence, I didn't sort of emphasize much. Again by independence, because the box is remaining the same at each draw, because I'm doing with replacement. It's a very important point I so they emphasize. So what happens is that this probability also becomes a binomial. It becomes like a k minus 1 successes in n minus 1 trials. So once you do that, you're on your way, because you can use the fact that probability of aj given bk is probability of aj and bk divided by probability bk. And now I can flip the conditional probability formula to give me bk and aj is bk given aj times probability aj. But this is value calculated. Probability bk given aj is from here. We've got this n minus 1 choose k minus 1, p to the k minus 1 times this guy, which I put at the top. aj is from here, w by m, which is called p. And here I got probability of bk, which is from the first line, second line, and then I got this n choose k, p power k. I cancel all off, I get k by m. So kind of a cute fact that if you do with replacement, moment at condition on the number of samples in n draws, what happens in each draw is the same probability. It's k by n. It's kind of a funky idea. Very good. Okay. I think question number 4 we can do. Let's see question number 4. You want to try? Let's do A maybe. I don't want to do B and C. But let's see. Have people done question number 4A? I'll just make it bigger so you can see it. Let's do 4A and then we'll try and. I want to do another interesting problem in 5 and 6. So let me try and solve 4A for you. So how does one do 4A? In 4A, the key thing is. Let me erase 4B. So what do I have to find? Let's say H is the event that student takes history. Okay. P is the event the student takes psychology. M is the event student takes mathematics. Maybe I'll come back to the third one a little later. Let me finish this problem. I'll come back. So now what do you have to find here? You have to find probability student takes history, psychology, but not mathematics. I'll put the notes up on the website. You can look at number 3 later as well. So what do you have to find? You have to find the probability of taking history and psychology, but not mathematics, right? And not mathematics, and common. This is what you're doing. Right. So how does one do this now? It's got to be a number less than 1. So I guess I don't know what you mean by 35. But how do you find it? So in such questions, what do you do typically? If you have a question like this, you're choosing equally likely. So what you do is you draw a Venn diagram. That's the best thing to do. Okay? So let's draw a Venn diagram. They can draw a Venn diagram. Let's make it bigger. Let me move this across. We come back to this. You want to find this, we come back to this. Let me copy it. So first thing you do is you draw a Venn diagram. Then the answer becomes immediate. There's nothing to be done after. So if I draw a Venn diagram, let me draw a big box that my entire thing is there. Okay. Let me draw people in mathematics as green. Okay. Let me draw people in history as blue. Okay. And let me draw psychology as black. Okay. So 0.5 seems a little too high. Right? Let's see if it comes out. Let's see. So let's try and go and see what's given to us. What's given to us is the following. Once you do this, it's clear. Sorry. Oh God. Very nice. So what do I know? Total is 100, right? Total is 100. I also, let's go from the back. 8 did not take any of these subjects. So let's say H is blue, right? What's green? Green is mathematics, I told. And my black is psychology. Right. So now I know 8 took nothing. So 8 are outside. So 8 are the red part. Very good. That's easy to see. Now I have, and how do I have, how many I have? I have 10 who did all 3. So 10 will be here. In this part, there will be 10. Right? So I'll put 10 here. So 10 did all 3. Very good. I know 25 did both mathematics, psychology. 25 will be in this entire black and this black and green will have 25 people, right? 25 did math and psychology. And then I have 15. So I have to see how many are here. So the whole thing is 25. So this will be 15 here. We'll come back to that second. And then I have 7 who studied history and neither mathematics nor psychology. So 7 are only history. And I have 22 that studied both mathematics and history. So this is 10. What's left here is just 12. And if this is 10, what's left here is, let me come back here. So, oh, sorry, let me come back here. If this is 10, if I write it properly, let me erase it properly. Let me see if I erase it. Very good. Oh no, you put it in green again. Oh. Okay, let me see if I can do it properly. Let me see if I can do this properly. Very good. So now, if I have 25 people here, this has got to be 15. Then here I have, how many do I have? I have history, psychology, and only psychology is how much? Is 68. Total 68. So 15 plus 10. Okay, we still have to do a little bit more work. But this is easy. 12, 10, 35. And this one, so I only have 5 left. Because I have 42 students mathematics. So 12 plus 10 is 22, 37. And I have 5 left. So I have 5. That's easy. So I have to find these two numbers. How do I find these two numbers? I know 68 studied psychology. I know 7 studied history and blah, blah. And 10 studied everybody, right? So how many are left now? That means if you think a little bit, you'll have 25 people in this corner. And what's left of 68 is just 18. It's 18 people. So once you have a Venn diagram, your probability is your solution is immediately clear. How to compute the problem. Very nice. So how does it compute the probability? Let me compute the probability now. Let me go down. So what do I want to compare? I'll leave this thing here like this. Right? So let me go to clipboard and place that here. This is what I want to compute. Right? So that's the same as, the first thing you observe is same as probability of H and M complement, that is people in history and not mathematics, subtracted from the probability of H and M complement, M union P complement. So M and P complement. M and P, sorry, M and P complement. Another complement. Sorry about that. I complement. The same as probability of H and M complement plus the probability of H and M and P complement. That's just a subtracting. Sorry. Very good. Once I do this, I'm in business now, because now this is the same as probability of H and M complement. I'll write it as probability of H plus probability of H and M, or minus probability, sorry, minus the probability of H and M and P complement. Now, if you look at the Venn diagram, let me just make it bigger so I can write the answer down. Look at the Venn diagram out of that. So that's going to be equal to, that's quite easy. This is just 50.54. Can work it out. This is just going to be 0.22, and this is going to be 0.7. 0.07. And your final answer is 0.25. That's the total people are 100. So whatever you do, you just have to go look at this thing and then divide by 100. That's the answer. We'll make it bigger now. We get this 2 pages down. Let me just go back up. So first was the Venn diagram that I draw. Once the Venn diagram was drawn, then the probability answer becomes quite easy. And these numbers I got was 0.54, 0.22, 0.07. I divide by 100, right? Because I have 7 here who are in history and not in mathematics, not in psychology. It's 7. That's 7 by 100. And this 22, this 22 by 100. That's these two guys. And this is 0.54. It's everybody in history. I hope this is clear. So in all these problems, they do the Venn diagram properly, then the whole calculation becomes immediately simple. There's no problem. Okay, very good. So let me spend 5 minutes doing 3 again, and then I'll come back and do, I'll show you guys 5 minutes. So let me go and explain 3 again, because someone wanted it. Let me try it again, one last time. So in 3, what happened? I'm choosing n balls with replacement, and I'm interested in finding the chance that I get jth ball is drawn in white, given that k balls drawn are white in the entire n sample. So the way I do that first is I understand probability of AJ is W by M, because that means that because every ball I'm drawing with replacement. So after I pick a ball, I put the ball back in. So the ball box composition doesn't change in the box. It's going to be W by M in every draw. That's clear. Then the chance of choosing K balls white in n draws, because I'm doing with replacement, each draw is independent. All it requires is K successes in n draws. So like a binomial experiment, you get n choose K, P power K, 1 minus P to the power n minus. Then I calculate the chance of getting K white balls in n draws, given jth ball drawn is white. That means jth ball is fixed. Jth draw is fixed. That's white. Then in the rest n minus 1 guys, to get total of K balls, I must get K minus 1 white balls. That's why this probability is the same as getting K minus 1 white balls in n minus 1 draw. Because if I want K white in n draws, and jth is white, given jth is white, is the same as this. And because of independence again, it's the same as n minus 1 choose K minus 1, P to the K minus 1, 1 minus P to the n minus 1 K minus 1. Then finally, I put all these 3 together because I know probability of AJ given BK is probability of AJ and BK divided probability of BK. And that's the same as probability of BK and AJ divided probability of BK. Same thing, no difference here. And this is the same as probability of BK given AJ times probability of AJ, reverse formula. And once I have this, I plug in all these 3 guys. I plug in W by M for P of AJ and so on and so forth. And I get this formula. Everything cancels off in algebra, and I get K by M. And the crucial thing is that the moment I fix K balls being white in n draws, the chance of getting a ball in the jth draw is just K by M. It doesn't depend on how the box is, it doesn't depend on what the draw is. That's the crucial point. Okay, very nice. Now let me try and show you a 5th problem. Let's try and do one more problem. Okay, we solved this first 4 problems. Let's solve one more. Let's solve 5, 6, 7. I may not be able to do 7. I will do 5 next. 5 and 6. Maybe we'll do 5 and 6 quickly. But, okay. So again, I think it's very nice that you're all asking questions and answers. It's very nice. But the idea is that in question number 6, you have to tell me which one has higher probability. Is it the 4-engine one or the 2-engine one? Which one will fly with in question number 6? In question number 5, I understand the number is big. Right. So let's think a little bit. 2-engine, 4-engine. Let's think a little bit. Okay. Let's try and do that. So in this, since I'm running short of time, I won't write the question down. I'll try and finish the problems. I hope you don't know the question. So question number 5 was I had to find out the probability. So this is the answer. So let me write the answer down. So what did I have to do? I had to find out the probability of innocent given the person was judged guilty. That's what I had to find. Very good. But that's the same like before, same as probability of innocent and judged guilty. Very good. I'll write the base theorem down, proper proof, so it's easy. Divided by probability of judge guilty. Now that's the same as, now you have to just flip the top, the reverse way, is the probability of judge guilty given innocent, right, times the probability of innocent. That's what the first top part. And the bottom part is judge guilty. So judge guilty is both judge guilty and innocent, and judge guilty and non-innocent. So let me cut and paste this thing. The bottom part, I'll write down. Sorry, I'm very bad at this. Let's see if I can get it done. Oh, come on. Okay, very right. So the probability of innocent and judge guilty and I'll just copy this. It's all I can't copy it. I'm writing straight line. Plus probability of not innocent. So I'll call it innocent complement and judge guilty. And that's the same as the whole thing. This remains the same. So I'll write in short form, probability of, I'll just say judge guilty as JG, given innocent as I, times probability of I, plus probability of judge guilty, given I complement, times probability of I complement. Where I is innocent and I complement innocent, and JG is judge guilty. And now that's the same as, now you know all the answers, right? Judge guilty given innocent from the problem is just going to be 0.01. I think that's the correct one. Innocent is 0.95. Right? And the whole thing divided by this again 0.01 times 0.95. The judge guilty given innocent complement, that's going to be 0.1 times 0.05. Very good. So this is just, let me make this color as perhaps as red. So this is red is like this. This is red. This part is here, and this part is make it green. This coloring is not coming correctly, but it's okay. You just understand it. This from here. Green, very nice. And top part is blue. So now this comes out to be, I think if you do the calculation, it's 0.17. So that will be the answer. So let me do a little bit more general problem for 6. A little bit more general problem. So let's say I tell you P is the probability that an engine fails. Okay, let's not take it as 0.2. Let's take it as P. Okay. Let's not take it as 0.2. Let's try and just take P is the engine fails. Okay. All engines are independent. So independence is also there. Every engine is independent. Okay. Let's do a blue calculation. Let's do a calculation that the 4-engine plane has a safe flight. Okay. A 4-engine plane has a safe flight. 4-engine plane has a safe flight. So let's say the probability of 4-engine plane. Okay. So that means what? You should not have more than you can have up to 2 engines can fail, right? So this can be written as 1 minus the chance, the probability that 3 engines fail. 3 engines fail. What happened? 3 engines fail minus the probability that 4 engines fail. All 4 fail. That's the same thing. So this you can write as 1 minus, this is just 3 engines, they're all independent. So you have 3 failures. So and each failure comes with probability P. So it's just 4 choose 3. P power 3 is P, and then 1 minus P to the power 4 minus 3 is 1. And this is just P power 4. That calculation is clear? Very good. Now, let me do the calculation that 2-engine plane fails. Probability that a 2-engine has a safe flight. What's that going to be? Again, I can do the same thing. It's 1 minus the probability that both engines fail. Because only if both engines fail, the that's okay. That's not a problem. So both engines fail, then two engines. Someone said it's on the assignment. That's not a problem. So now this is going to be equal to what? 1 minus this guy is both engines fail. That's just p squared. So that part is clear. So now, when do you think a 2-engine plane is safer and a 4-engine plane safer? When the green probability is bigger than the blue probability, that means the 2-engine plane is safer. If the blue is bigger than the green, then the 4-engine plane is safe, right? So let me write down. So the so let's see. So I just write down blue is bigger. I say blue is bigger than green. Keep it like this. Blue is bigger than green. That means that the 2-engine plane is not as safe as the 4-engine one. You'd rather go with the 4-engine one. That happens if and only if. What happens if and only if? What's the blue part? Blue part is 1 minus 4 choose 3. That's just 4 p cubed and 1 minus p to the power 4. That's the blue part, blue probability. And bigger than the green. The green is 1 minus p squared. And that's if and only if. What happens? We make this in black color. Black. Make this in black. Make this also in black. Very good. That when that happens, here I can cancel off the 1 on both sides. Right? That happens when if and only if I have p squared, I can cancel off p squared on both sides. So I can get, let's say I go like this, p squared here. I'll have 2 left. I'll have 1 left. Right? So if and only if minus 4 p into 1 minus p squared is bigger than minus 1. Is that your? So that you rewrite it properly, you just get p squared. So this is a condition on p that tells you when the blue engine will be safer than the green engine, the 2-engine plane. So 4-engine plane, safer than 2-engine plane. This condition. So you put p equal to 0.2. So take p equal to 0.2. And then you find minus 4 into 0.2 into 0.8 minus 0.2 whole squared has to be minus 1. And it will. Right? And this is true. It's true. So in this example, the 4-engine plane is safer than the 2-engine plane. Very good. In general, you can find a condition on P when this calculation is true. What's the condition on P? This if and only if. What should I write about P here? Right? So I want to write something about P. What do I write? Bigger than or less than something. What do I write? Let's say P is bigger than something. What should I write here? 0.25? No, may not be. 1/4? May not. I don't think that's correct. Let's think a little bit. So work out the quadratic, right? So it's p squared. So it's minus 4p minus 5p squared. So minus plus 4p minus p squared, 3p squared, minus 4p minus 1, right? Let's do green, let's say. So 3p squared, right? That's here, because minus 4p minus p squared. We have minus 4p, and we have a plus 1 is positive, right? That's what this is. If only if this happens, and that happens when. How do you solve this quadratic? How do you solve this step? Let me move this down. Roots, okay, you know how to find, how do you find roots? You don't have to find roots, just you have to find the inequality, right? So you just do like 3p squared minus 4p, right? Minus 3p minus p plus 1 is positive. The same thing. So that's same as saying 3p into p minus 1 minus 1 into p minus 1 is positive, right? Let me move this down a little bit more. Let me take this across. Let me take it across. So let me move it down. So what happens here? That's if only what happens. This you can factorize again as 3p minus 1 into p minus 1 is positive. Have I got it correctly or have I got it wrong? No, this is correct. So you will get the fact that p is less than 1/3. Or at least 1/3. So p is at least 1/3. I made a mistake here in the calculation. Let me just check. I may have made a mistake calculation. I think I made a mistake in calculation. Let me just check here. Let me go back here. So that 1 minus 4p cubed, 1 minus, that's correct. Minus p power 4, that's correct. Very good. This one. So I cancel off. Let me do it slowly. Let me come back here. So I cancel off the 1. I get minus 1. I get p squared everywhere. I get p. Very good. So I get plus 4p squared minus p squared at 3p squared minus 4p plus 1 is positive. So 3p squared minus 3 blah 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 is positive. 3p squared is this. Right. So yeah, so I have to be careful here. So that means I come here. So now p is always less than 1 because p is a probability. That's an important point. That means this is in orange. And I know that means 3p minus 1 has to be negative. Because otherwise this is never positive. And that means that p is less than 1/3. So as long as p is less than 1/3, the 4-engine plane is safer. If p is bigger than 1/3, then the 2-engine plane is safer. That's kind of the interesting fact of this problem. Here 0.2 is less than 0.3, so your 4-engine plane is safer. So the key fact is that p is less than 1/3 is if and only if that same thing is that probability of 4-engine plane is safe is bigger than the probability that the 2-engine plane is safe. So in our case, p was 0.2, so hold on. Let me recap. So the idea was that you compute the chance that the probability of the 4-engine plane is safe. That comes out to be like a binomial probability because each engine is independent. So it's 1 minus the probability that 3-engine fails or 4-engine fails. So 1 minus 4 choose 3, p cubed, 1 minus p, minus p power. You can get this side. Very good. On the left hand side, that's correct. Then you go and see what the probability 2-engine plane is. That's just 1 minus p squared. And then you want to see when is the 4-engine plane safer than the 2-engine plane. You do this calculation and you get p is 1/3. That means if p is less than 1/3, that's if and only if the probability of the 4-engine plane is safe is bigger than the probability. So if p is less than 1/3, you want to go on the 2-engine plane. If p is bigger than 1/3, so if p is less than 1/3, you want to go on the 4-engine plane. If p is bigger than or equal to 1/3, then you want to go in the, you can go on equal to 1/3, you can go on either plane, and bigger than 1/3, you want to go on the 2-engine plane. Okay, very good.